Hello guys, and welcome back to the third week, second class. And we talked about the fundamental basics for the x86 assembly language in terms of programming. And we're going to continue where we stopped last time, which is duplication, the DUP. So we're talking about memory. So we know how to declare data types. So like the D word, and we learn about the word and then the byte. These are for the unsigned, and then we add the S for each, right? Like the D word, the S word. So together it's like one thing. And the byte. So this is for the unsigned, this is for the signed. And we know the little Endian as well. I will emphasize this just in a second, right? And we're going to continue on the duplication. So how can we duplicate a memory? All right. So what if I want to declare a memory of a size 200, right? So we are not going to declare it like in terms of a list. We talked about a list, right? We say byte, and then we're going to say 2, 3, 4, and then we're going to go to the 200. That is too much. Or maybe I'm going to say B. It's also a byte word or D word, and then I'm going to say 0, 0, 0, 200, right? So if I want to initialize 200 space that I can access using the variable name right here, it's going to be too much. So to solve this problem, we are using duplicate. So right here we say create a memory, and this memory is pointed at by variable or var1, and this var1 points at the first byte, and we can access, in addition to this, around 20 bytes next to it. So it's just gonna say var1 plus 1, and then var1 plus 2, and then this, if you wanna access this, plus 3, and so on and so forth, okay? So these are the way you do it. So if you have it, you have the counter, that is the counter, and then the keyword, and then the argument. We need to initialize it with 0 or question mark. So you have the variable name, the data type, and then the counter, and then the duplications, and then this is the argument. Okay, so what if here you said, I need to duplicate this space, stack. So remember, each ASCII is a 1 byte, right? So if you want to do this, you are saying what? You're saying, I want to have this 4 times, and each is of what? 1 byte size. So if you do this one, you're going to have S, T, A, C, K. This is 1 byte, 2 byte, 3 byte, 4 byte, 5 byte. And then you're going to do it 4 times. So you're going to do this, and then you're going to do this, and then you're going to do this, and you're going to do this 4 times. Okay? If the value right here it just was A, then you're going to find it A. So that happens to be 5 because the string is of 5 bytes, right? So 4 times of size 5. Okay? And this part right here, you have a memory that is var4. And in this memory, you're going to have what? This is here. You're going to have 10, a byte, 3 is a byte. And then we have what from here? We have duplication, right? We say, sorry, let's say duplication 3. I'm sorry, this is 3. Okay, so this is the whole thing 3. So you're going to say 3 assign 0, 3 bytes, each assign 0. So that's the count, how many space you want to create. So this is 10, 1 value, and then this is duplication. So this is 1. And then after that, we have 20. So if I ask you the size of this memory, is going to be 5 bytes. Why this is 20 bytes? Because this is 5 by 4. It's going to be 20. Okay, so this is the duplication. So you can use it to save yourself some time initializing a memory, just saying 0, 0, 0, 20 times, right? Just gonna say the count, how many space. You can do it for the word. You can say, let's say var1, and then you can say word, and then you're gonna say 3. That's how many times you need to repeat the word memory. Okay, and then you're going to say the duplication and initialize it with 0. So remember, a word is a space of 2 bytes. So you're going to create a space of 2 bytes how many times? 3 times. You see it? So this is 2 plus 2 plus 2. So the entire thing is going to be 3 by 2 is going to be 6 byte in terms of bytes, okay? And these are the same applies, right? For the word, whatever we talks about, we explain for the byte is applied for the word and D word. So this is word and this is S word. Okay, so you can assign a byte, 2 bytes, sorry. Each ASCII is a byte. So this is a word. And you can do this with a byte, right? You can say B is a byte, right? And then you can assign it only A. But if you want to assign AB, then you need a word. So that's why we do it right here. This is my last word, and then we have to assign 1, 2, 3, 4, 5. So what is the size of this word? I know that the space is going to be 2 each, right? So we're going to have 0, 1, 0, 0. That is the first part, which is my list for short. And then we're going to have 0, 2, 0, 0. And then we're going to have 0, 3, 0, 0. And then we're going to have 0, 4, 0, 0. And then I'm talking about this part, okay? And then we're gonna have 0, 5, 0, 0, okay? So this is 0, this is 2, this is 4, this is 6, this is what? 8. So if you wanna access this 4 right here, you're gonna say move to EX because it's a word, right? And then we're gonna say my less plus what? Plus 6. So this is 0 plus 6, you're gonna go right here. So AX is going to have 0, 4, 0, 0. You see, it's going to have this value. Okay, this is a word, duplication 5. So 5 by 2 is going to be what? In total, 10 bytes, okay, but is divided by 2. So this is the first part. This is the second. This is the third. So this is like the first word, the second word, the third word, and so on and so forth. And we're going to have them 0, 0. So that's going to be my array. And then this is going to be 0, 2, 4, 6, and that is the way we do offsetting. We're going to talk about offsetting later. Okay, but remember this is unsigned and this is a signed value. Okay, these are applies for the quad word. Okay, so if you have a quad word, we know the quad word is going to be how many bytes? This is going to be 1, 2, 3, 4, 5, 6, 7, 8. So it's going to be 8 by 8. So this is going to be what? 64 bits, right? So this is a quad word. Not going to talk about the reals. We're going to talk about them later. But this is the quad word. And if you want to store this in the memory, these each is a byte, right? It's going to be little Indian, so we're going to go right to left. So we're going to store 78, 56, 34, 12, 78, 56, 34, 12. So this is going to be your memory. This is just one memory. Okay, and this memory you're pointing at with quad 1. If you need to have another memory, it's going to be next to it. So this is going to be what? 8, 0, and this is going to be 8. 0 plus 8, you're going to go to the other memory, which is going to be 1, 2, 3, 4, 5, 6, 7, 8 bytes. Okay, so this, if you want to access this memory, you're just going to say quad 1 plus 8. This is plus 0. It's just the quad. Okay? And this is what we call the TBYTE. TBYTE is a very unique memory, okay? So the TBYTE, T means stands for 10. So you're going to have 10 bytes right here. Okay? So for the 10 bytes right here, this is the number. How you're going to store the number is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and it's in a hex. All right, and the TBYTE is not stored using the 2's complement system. Okay, it's stored using the BCD digit. And I assume you know this in the introduction to computer science class or introduction to computing class. And when we talk about BCD, we have 2 types of BCD. Okay, BCD that is packet and the impact. The packed BCD is just like if you have a 12 right here, so you're just going to have 0, 0, 0, sorry, 0, 0, 1, 0, and then you have 0, 0, 0, 1. So this is 1 and this is 2, that's 12. Okay, so with 2 digits, with 2 hexadecimal digits, you can represent any number, any decimal number, right? That's more than enough. Or impact, that's going to take the entire byte. Why I have to waste this space if I can represent, if all I need just like 4 bits, right? 8 bits right here. Okay, 4 bits each. So that's the BCD system. Okay, this is the 96. You can represent it 96 in the packed format, or the impact 000. This is 9, 000, and this is what 6, right? So the digit takes 8 bits. It takes a byte. The digit here takes what? 4 bits have a byte. So the entire number takes a byte. Okay, this is the entire numbers takes 2 bytes. So that takes more space. So the TBYTE use the packed BCD. Okay, and so this is 2 to the power 10. That's a crazy number. Okay, so we're going to look at how the TBYTE is really stored because it's not 2's complement. So if it's not a two's complement, then how the negative numbers are really represented. So this is when it is in the memory. It's in the real memory. It's not where you declare it on the editor, right? So if you look at this number in the real memory, the last byte right here is 0, 0. That means it's positive. The last byte right here, it's 8, 0. So that means 1, 0, 0, 0, 0, 0, 0, 0. This is 8, 0, right? So that shows you like this number is negative. So the way you say this number is negative, you present it in this way. So this is little Endian. You store 3 first, and then 2, and then 0, 0, 0, 0. The last byte, make it 8, 0 if it's negative number, or the last byte 0, 0 if the number is what? If it is a positive value. So this is invalid. If you look at this number, this is invalid. Can you think about it why this is invalid? Can you think about it? Okay, so this is valid and this part is invalid, okay? So why this is invalid? Because here you represent the negative using the sign, so that's the two's complement. And TBYTE does not go with the two's complement, it goes with the BCD integer and packet, right? So if you want to say this number is negative, write it in this way. So remember, this is in the editor, okay? The one that we talked about before was represented in the memory. So if you want to look at this in the memory, it is going to be 3, 4, 1, 2, and then 0, 0, 3, 4, 5, 6, 7, 8, 9, and the last number is going to be 8, 0. If it is vertical or horizontal, it's going to be in this way. But this is in the editor. When you write it in editor, you can do it in this way. Okay? Is that kind of clear? And that's when I talked about the little Endian. So how you store data. So this is very important, guys. How you store data in a register like EAX, and how you store data in a memory. Okay, let's say like val1. So we know that the registers are go from right to left. We know it from the first lab, right? So 0 to 31, these are 32-bit. We have the first byte here, the second byte, the third byte, the fourth byte. And this is the memory. It depends on the space, how you divide this space. We divide this space by 4. So this is 1, 2, 3, 4. That is the first space. And then this is 1, 2, 3, 4. That is 0. That is 4. If it's word, then that is 0. That's 2. If it's quad word, then that's a 0. That's 8. So we go with the blocks. Okay, so this is a block of memory. Okay, so if you store this number, you see like 7, 8 was first, 5, 6, 3, 4, and 1, 2. I explained that already on the Visual Studio, so it should be clear for you right now, okay? So this is like another way to represent the little Endian, okay? So there is the big Endian. If it's a big Endian, that's not x86. x86 does not work in the big Endian, but if you want to know the big Endian is, it goes in the way the English language work, okay? The way the English language works. It's going to go from right to left, okay? But this is not how x86 works. Okay? This is a simple program. You're going to play with a similar program in the lab, but this is like a simple program that has 2 variables right here. 3 variables, I'm sorry, and then the sum. So you need to add first to second to third. So you first move the first value to EAX. Why we did that? Why we did not add first to second right away? Why we did not say add first to the second? Because this is memory to memory. We cannot add memory to memory. We can add immediate to memory. We can add register to memory. We can add memory to register. You see what I'm talking about? But we cannot do memory to memory. That's not allowed. So we have to move something to a register first. So we move this one to a register. And then we add second to a register. That's memory to a register. That's fine. And then that is memory to a register. That's fine. So we move first, and then we add second, and then we add the third. And then now once we're done, we have the result in EAX. We need to move it where? To the space that we reserved, which is sum. So move sum to the, move EAX to the sum. Remember, this is the destination. This is the source, always. Okay, so play with this example. You have it even in the lab anyway, but if you want to do it right now, that's fine. Okay, so there is another thing that I would like to talk about, which is uninitialized data. I'll explain that in a second. So when you look at this data right here, you have D word, and it is going to be 10. We have to count space of 10, right? And each block is D word. So 10 by 4. So we have the first 4 bytes, 1, 2, 3, 4, and we're going to have 10 of those. Okay, 1, 2, 3, 4. Okay, 10 of those. So 10 by 4, we're going to have 40 bytes space right here, 40 bytes. For this one, it's going to be 5,000 by 4, then it's going to be 20,000 bytes. So when you create this space, if you want to avoid wasting the executable file, because in the executable file, you're going to create a space that has 20,000 bytes declared in the executable, and your executable file is going to be really large. Okay, so if you want to avoid this problem, you're just going to say .data ? So when you do this 20,000 bytes, they are not going to be initialized inside your executable file. They're going to be initialized when you load the executable file to the memory. So in the hard disk, you're just going to have like 4 bytes initialized in the hard disk file. And when you load it, you're going to have more space. So this is the executable file size is reduced when you do it in this way. Okay? So as I said, assembly is all about performance, right? So if you need more control, you need assembly. Okay? So here we're talking about constants. We have talking about integers. We talked about strings. So how we declare integer. This is the way we declare integers in a high-level language, right, guys? We say final. You might wonder why final, and then that's the type, that's the variable name, and that's the value, right? So this is the same. We're always going to say final. Final means that we are not going to change things at the runtime. So we have the same thing in assembly language. So we have the equal sign. We're going to cover this. If you are interested in these, just go to the refer to the book. The reason why I don't want to cover these, because those directives are similar to the high-level languages, and I don't think so I'm going to teach you something new if we're talking about a high-level languages, okay? So if you look at this example right here, it uses storage. If we use symbol, right here, what I mean by the symbol or symbolic constants, that's the assembly. Uses storage, no. The variable, yes, because the variable, we're going to say A byte 5 or B word 6. So this takes 1 byte, this takes 2 bytes, right? So it takes storage, but the symbolic does not take storage. What do you mean? We're talking about the main memory. So in the main memory, it's not going to take storage. Value change at the runtime? No, that's possible. So why we say constants does not reserve storage? Remember the word final that you use in Java? What final means? That means it's not going to go to your main memory. It has a special memory that's out of your program's memory, okay? So if you look at it right here in assembly, we say count equal to 500. So this is going to go to a special memory, and sometimes this is going to move to a specific register. So that's why it's not part of your main memory, okay? So if we talk about like the list that we have right here, so we have a list. This is my list. And remember, list always points at the first byte. It doesn't see the rest. So this is 10, 20, 30, 40. So if you're going to say move to AL, because AL is a byte, we're going to say list. I'm sorry. We are moving this, but what if we want to move this? So this is a byte. We go by 0, 1, 2. So we're going to say move list plus 2. We're going to move 30. Okay. If this happens to be a word, then it's going to be, this is the first block. This is the second block. This is the third block. And this is the fourth block. Okay. So this is going to be 0, but this is not 1. This is 2 because you have to cross 2, right? It's a word. 4 and 6. If it's a D word, it's going to be 0, 4, 8, 12, and so on and so forth. So for this, the size is what? 4. So we're going to say declare a constant. What if we say 50 and 60, right? We're going to come back and remove this and make it 6, right? So can we do this dynamically? So we're going to learn a very interesting concepts, right? That's going to help us do this one dynamically, but we need to learn something new. So how are we going to do this one dynamically? We're going to do it using the operator, right? The $sign operator. That's what we call the current location counter. This is a hidden operator that you can powerfully use to achieve specific things, such as knowing the size of an array or a list, okay? So this is what the current location is. So if you want to compute the size, instead of saying 4, you're just going to make it what? Make it dynamic. So if you keep it this way, it's going to be 4. If you add, it's going to be whatever the size is. So as I said, if this is the list, and this is the space that you have, so you have 10, and you have 20, and you have 30, and you have 40, right? So if this is what you have right here, the dollar sign points right here. That is the end, right? And the list is right here. So this is 0, 1, 2, 3, right? So if you want to count this, you are actually saying the dollar sign, which is the current location, that is the current location, the last element you have in the list. And you're going to say the current location here minus what? Minus less. So you're taking this from this. Okay, so this is going to be number 4, right? So if you say 4 minus 0, you're going to get 4. So the size is 4. If you add another element here, you say 50. This happens to be the case, 50. Then the current location pointing here. So 5 minus 0 is going to be 5. So it's going to be dynamic all the time. Okay? So this method has some tricks I would like you to pay attention to, because the current moves not for this variable, for your entire memory. So if you have a memory like the one we have right here, okay? Let me see if I can erase. Okay, so if I can erase this part. Okay, all right, so this is gone. Okay, so let's say if you are actually right here and you have less, and then you added what, 20 bytes. So you come in here and you create a var2, that is var2, it points at this byte, and it goes up to number 20th, okay? So this is the 20th. And then after that, now you say, I want to compute the size of this. So this is 1, 2, 3, 4. But we are getting the value, what? 24. Why? Because the dollar sign is going to move as long as you are moving within your memory. So it's not connected with the list, it's connected with the entire memory. So if you say it right here, it's going to be what? It's going to be 24, because these are 4 and this is 20. So this 24 minus 0 is going to give you 24. But in fact, you only have 4. The problem is that you have another memory between the memory that you need to compute at a size and the list or the constant declaration. So to solve this problem, you have to put this one right here. If you put this one right here, at this point, the dollar sign points here. So it's going to give you the right size. And then once you move this one here, then it's going to continue from there. At the end, the dollar sign is going to go to the 20. Okay? So this is something that you need to keep in mind. You see it becomes very handy how we can compute this. We can count it 1, 2, 3, 4, 5, 6, and so on, but we can use the current location. So the current location should point at this, right? The last thing that you have. And you know that this my string points at the first byte. So subtracting this from this is going to give you the string, right? The length, right? So that's what you do. That is the dollar sign and then my string. You subtract this from this is going to give you the length. Okay, this is the same. But here it's a word. Remember, if it's a word, it's going to count byte by byte. But actually, this is 1, 2, 3, 4 elements. If you use the dollar sign without this 2, it's going to tell you that how many elements you have in here. It's not going to say 4, it's going to say 8 because it counts by byte. So if we want to really know the number of elements in this list in terms of a word, so we have to divide by 2. In terms of a D word, no brainer, right? You just divide by 4 and so on and so forth. If you don't divide by 4, it's going to say, hey, you have 16 words in here, D words in here, but we only have 4. Okay? So this is a very helpful sign. Just keep that in mind. We're going to use it later when we talk about the arrays. Okay? So now we're going to look at the 64-bit programs. So we have been talking about the 32-bit, the 386. So you're going to have a lab this week. And in this lab, we're going to cover this part in more details. But I'm just going to introduce the big picture of the 64-bit. So in the 64-bit, we need to get rid of this because this says 32-bit. We already covered this, right, in the last class, chapter 3, right? All right, so we can, if we get rid of this, then we're going to have a completely different program. Okay, so keep that in mind. This is going to go, the 386, the model is going to go, the stack is going to go. Can we have a program without a stack? Yes, this stack is going to be defined automatically. And we're going to what? We're going to look at the invoke. The invoke is not going to be there. We're going to use something we call call because the model used the standard call, right? And the standard call is what? Is invoke. It uses invoke. If you remember here, that is the standard call. Okay, so that uses invoke here. But now we're going to use a call. So the call here is completely different. It uses different standards. So this is like when you say some quad word, we know this is 64-bit, right? in order to store this in EAX is not possible because this is 32-bit, right? So you need a 64-bit program, right? So if you want to do this, you can easily move 5 to racks. We already covered that in the architecture of x86. And then you add 6 to racks, right? So you get the result 11. Then move 11, which is 64-bit, to the sum. And that is going to go very handy. Okay, so if you look at it right here, we have a quad word. Instead of EAX, we have the racks. Okay, and these are already gone. We don't have them. Okay, and even this part is no longer there. And even this part is no longer there. So you're going to see a specific program, use it only one time in the lab and then take it away, because that is something some of my students do. The next lab, they're going to use the 64-bit program. No, we're just going to do it one lab and that's it. Okay, so that way you're going to see what 64-bit programming is all about. Okay. So now we're going to talk about like the main concept right here, which is listing files. We're going to talk about what's listing files. So we know this in general, right? So if you have the source file, the text file in assembly, and you pass it to the assembler. So this is the first thing, you write the code and everything, you pass it to the assembler, you get the objective file. And with the help of the linker, you're going to link the library, like invoke and call and so on. And then you're going to produce the executable. So when you have the executable, you have a human reading part or readable file, similar to the executable we call map file, okay? And we also, objective file, we can read it by looking at what the listing file. So this is our focus. So this is gonna happen by configuring your Visual Studio. So you're gonna do this in the lab as well. So you're gonna play with this part in the lab. But let me introduce the main concept for this part. So when you open the file in the lab, this is what you should see. Okay, so when you look at the lab right here, you're going to see this is your program, but this is the objective file. Remember, this is the objective file. Okay, the entire objective file. So this is your source code, but your source code now is translated into the objective file. So this is mainly actually the objective file. So in your objective file, each line has an address. So these are details for the linker, because the linker takes the objective file and produces the executable. So these are, if you notice, 1 byte, 2 byte, 3 byte, 4 bytes. So these 4 bytes, it's going to be 32-bit, right? And that makes sense because we are dealing with a 32-bit program. So if you look at the dot code right here, it doesn't have a translation. But if you look at the move, it has a translation. And we already said directives, main, dot code, invoke, they don't have, they are not instructions. So if they are not instructions, then they don't have instruction set equivalents, right? So this is an instruction, push. Call is an instruction, invoke is not. Main and in, these are not instructions. So that's why you don't see instruction code for them. So if you look at this, this is the machine code. B0, that's for move. And this is EAX5. So EAX, it seems, is encoded as 000000, and the 5 is the immediate. Okay? And this is add. In this add, the EAX is being encoded differently. So this is add 83 and C0. So these, it seems that they encoded together. If we have the time at the end of the semester, I'm gonna spend some time. I did this twice during the past 3 years when I talk about encoding, instruction encoding, okay? But the rest of it, I didn't have the time to cover it because we are always running out of time. We have a lot to cover. This is the instruction code for push. This is the instruction code for E8. So if you are confused, I'm not going to ask you what every byte means. You're just going to say the translation or the instruction or the machine code for this instruction is this. Okay? And in the example in the lab, you will notice that I will ask you about the difference that the question is in the lab is set up to show you like the register name. It could be encoded differently based on the instructions used, okay? And there is something interesting here. These are all 00 and this is 5. And right here, when we say address, at the assembly time, we don't really know the details, right? We don't know, we are not loading, we are just producing the executable. We're just creating a file in the hard disk, right? So we don't know, like you calling a hotel and you said, hey, 3 years from now, I'm gonna come and then I'm gonna live in the room number 11. They tell you, you know what, we're gonna reserve, you're gonna have a reservation for you that you're gonna live in a room, but we are not gonna promise room number 5 because we don't know at that time, at that state, what the situation is. This is exactly the same for the assembler. The assembler doesn't know yet. So just gonna ask for a 32-bit register, but why these are all 00 and this is 5? And this is 8. So this is not a register, this is an offset. I'll explain that in a minute. So if you look at the line right here, that explains like every part. That's the line number, that is the offset, the one right here is the offset, and so on and so forth. That's the source line, and so on and so forth, okay? So these are the parts right here, like for this instruction, the line number, the offset, the machine code, and this is the source line. If there's any nesting, that's the space. Okay, so the source line, such as the comments, do not generate any offset. So comments, .code, directives, they're not going to generate any offsets, right? And we know why, right? And so this is very important. Just look at this part right here, and you're going to play with this in the lab. The only thing that I'm going to explain right here is the 5, 8, and this part, right? So why we have a 5 right here? So if you count the size of this instruction, 0, 1 byte, 2 byte, 3 byte, 4 byte, right? So this is 1, 2, 3, 4, 5 bytes. So after 5 bytes, you're gonna find the next instruction. That's how the instruction pointers work. Points right here, if it wanna go to the next instruction, is gonna add 5 to the 0. Add 5 to this 0, it's gonna go right here, and that's the next instruction. If it's gonna go to the next instruction, then this is 5, 6, 7, 8. So if it's right here or right here, and it add 3 to this, is gonna be what? It's gonna be 8, right? So we're gonna go to this one, 8. If you are right here and you have 2 bytes in here, 2 plus what? 8, you're gonna get 10. Like 5 plus 0, you're gonna get 5. And then the 3 plus 5, you're gonna get 8. And 2 plus 8, you're gonna have what? 10. And 10 plus 1, 2, 3, 4, 5 is gonna be 15, F. So this is always the offset. It's gonna tell the instruction pointer where to go next, okay? So this is what it is, and I explained that in more details on this side, all right? Okay, so that is that. So that is the .listing file, and this is actually the map file. Okay, if you look at the executable, that one is the .listing, is a human readable way of the objective file. If you look at the objective file, plain objective file is really hard to read because it's made to be read by the linker. But if you want to read the objective file in a very easy way, then try to look at the .listing file. In the .listing file, you're going to learn details that's going to help your understanding of how a program is going to be actually translated from one format to the other. If you want to look at the executable, it's all zeros and ones. It's really hard to read. So another human readable way that the Visual Studio produce is the map. So if you look at this program right here, this is the executable, but no zeros and ones. It's all readable things that as a human we can read, right? Especially if you know assembly. So this is the .code, this is the .data, this is the .stack. So here it says it starts at that location, it ends at that location. That's what really matters. That's the length of the program, okay? And that's the segment. This is the length of the program. So the amount of the space that the program is gonna take is gonna be 1C. And if you say this is 001, and C means what? 12, right? So it's going to be 1, 1, 0, 0. So if you say 1, 2, 4, 8, 16, so you cannot have 16 plus 8 plus 4, right? So this is 18, so 20 bytes. So the executable, the .code, takes 20 bytes of space. If you look at this data 1A, so this is going to be 0001, 1010. This is 1, 2, 4, 8, 16. So this is going to be 16 and 8 and 2, right? So this is going to be 20. So this is going to take 20 bytes. So it tells you the .data is taking 20 bytes. Maybe you're declaring some variables there that they're going to take 20 bytes, and so on and so forth. So the .stack right now, it takes what right here? It takes like a large space, right? If you look at it, this is going to be 0000, right? So this is going to be your 256, right? And then you have another 0. This is 256, right? And then you have a 1 in here. Okay, so this is gonna be, if you calculate this, you're gonna like have a 4096 almost bytes for the .stack. So this is what you're gonna have in the map file, okay? So with that, I hope now you understand the fundamental of the assembly language program. You know why 32-bit, you know the elements, you know the mnemonics, you know how to declare variables, you know the data type, sign and unsign, you know the little Endian, you know how the data is stored in there, So you already know how to declare constants, and then you have a background about moving from memory to register, register to memory. And then we have the chance to look at the 64-bit program, and then what is an objective file, what's an executable file. I think you're ready now to start chapter 4, and that's what we're gonna cover in the week number 4. Okay, and by now I hope you are gonna be ready to do your lab number 3. And I also hope that you're gonna be ready for your chapter 4. So this chapter is very, very important. So you need to pay more attention to it, okay? Thank you for now, guys, and see you during the office hours.